Okay, can you see the slides? All right. Okay, thanks. Okay, let's continue. All right, yesterday we have discussed the continuation on intrinsic and extrinsic semiconductors. And we have also seen and discussed about shallow and deep impurities and how deep impurities are detrimental to our semiconductor devices. So just to recap, examples of shallow impurities are our dopants, like the one that we incorporate from group 5 and group 3 in order to make our silicon more N-type or more P-type. Okay, so those are shallow dopants which only require around 0.02 electron volt in order to completely ionize. And the energy state of the shallow dopants are very close to either conduction band age or valence band age. So they are pretty close to the band ages. Okay. On the other hand, if you talk about deep impurities, they are sitting deeper in the forbidden gap. Okay, they are close to the mid gap. For example, if you talk about deep impurities, so they can be like rare metals. They can also be like iron, copper, nickel, gold, right, and many more. Okay, so you can see the position of the energy states of the deep impurities in this below illustration, right? So deep impurities will represent as trap states or recombination centers in the band gap, which will eventually suck your electron hole and force them to recombine in a process that we call annihilation. So as a result, your carriers will be removed from your semiconductor and will affect your semiconductor operation badly. We have also discussed about the position of the Fermi level when we do our doping. On the left hand side, we have seen that when you dope your silicon to be more N-type, your position of the EF will be moving upwards, closer to the conduction band age. And on the other hand, if you dope your silicon to make it more P-type, your Fermi level will be reduced, will be going lower, closer to the band age of the valence band. So it's going to move in what we call in steps, right? So the higher doping level is going to move closer and closer and closer to the band age. So we've also discussed about law of mass action, where we firstly saw about the estimation or the approximation of the N or P to be close to the values of your doping levels. N will be approximately equal to ND when ND is way higher than NI. So for example, if you dope your silicon with phosphorus, which is ND, to the level of 10 to the 17, for example, and when 1017 is way higher than 10 to the 10, which is the Ni, so then your density of the free electrons can be approximated to be equal as Nd. So this is also applicable for P-type when you dope your silicon by boron or gallium. So when the doping level is high enough and way higher than Ni, which is equal to 10 to the 10, then your P can be approximated as Na, right? And we have also learned that Np is equal to Ni squared. So whenever you know your N or your P, for example, as your majority carriers, you can use equation of NP equals NS squared to be able to calculate your minority carrier. Okay, so recall that in N-type silicon or N-type semiconductor, electron is the majority carrier and hole is the minority carrier. And in P-type silicon or other P-type semiconductors, your hole will be your majority carrier and your electron will be your minority carrier. So now let's look at equations in order for us to calculate electron hole concentration at equilibrium. Okay, so this will be given by this below equation. So we have learned before that in order to calculate our density of free electrons or free holes, we need to use this equation at the top. Okay, where n naught here means equilibrium. So n is density of free electrons at equilibrium, n naught. So we need to integrate from EC, which is the, I forgot to bring my pen today. Now in the office. But anyway, okay, you need to integrate from, if you look at the density of states last time, so the shape is like that, right? The shape is like that. You can draw your density of states. The energy is on the y-axis, and you can draw your density of states like that. Half of the dome, inverted dome, and then dome shape for the valence band. Then, in order to calculate the density of free electrons in the conduction band, we need to integrate from the edge of conduction band, right? At the minimum point of conduction band to infinite, right? Going up infinitely. So that will be integration from EC up to infinite. And you need to multiply your Fermi Dirac distribution function, which is Fe. We've learned last time, where Fe is equal to 1 over 1 plus exponential E minus EF over KT. So your Fe will need to be multiplied with your density of states in the conduction band, or NCE, right? So this NE here is referring to NCE, so DE, right? So if you plug this in, it'll be simplified to N naught down here equals to NC, the density of states in the conduction band, exponential of simplified version of your Fermi Dirac distribution function, negative EC minus EF over KT. So that will give you density of free electrons in equilibrium. Okay, so N naught, density of free electrons, naught is for equilibrium condition. So you need to know the density of free electrons and free holes in equilibrium first before we start doing anything to the system or to the semiconductor material. So we need to know the original condition, which is the thermal equilibrium condition. So on the other hand, we do the very same thing to hole as well. So density of free hole here is equal to P naught. Okay, the very same thing. So you need to integrate from the conduction band H or valence band, which is at the top, down to negative infinite. Fe will be equal to Fermi Dirac distribution function as well for hole, and Pe will be the density of states of hole in the valence band. You can write as NVE, you can write it as PE, as long as you know what do you write down. Okay. So this will be simplified to P naught equals to NV, density of states in the valence band, times exponential term, negative EF minus EV over KT. So that will give you density of free holes at thermal equilibrium. Right, so for the calculation, you need to look at the value of NC and NV given by this table. So for example, if you look at silicon, so your NC will be equal to 2.8 times 10 to the 19. And for NV, for silicon, 1.04 times 10 to the 19. Okay, so then you can also see for gallium arsenide, for germanium, and for some other materials as well. Okay, so now you know how to calculate the density of free electrons and free holes at thermal equilibrium. So now let's move to a degenerate semiconductor. So what is a degenerate semiconductor? A degenerate semiconductor is a semiconductor with high doping level. So the key word here is high doping level. Okay, high doping level. that the material starts to act more like a metal than as a semiconductor. So a degenerate semiconductor is still a semiconductor that is heavily doped, right? That is heavily doped. Or when? How high? Okay, how high? Let's see later on. Okay. So it has to be doped high enough to be qualified or to be called as degenerate semiconductor. So at that point, the behavior of the semiconductor is just like metal. So the behavior is like metal, but it is still essentially a semiconductor material. So that basically means it is a semiconductor with a very high electrical conductivity owing to the high doping level, okay? So this happens when the doping concentration becomes equal or larger than the corresponding effective density of states, okay? The doping concentration becomes equal or larger than the corresponding effective density of states. So how do you tell? You can always come back to this table and check. For example, for silicon, okay, if you dope it to make it more n-type, so you look at the density of states of your conduction band, so that is equal to 2.8 times 10 to the 19. So if your doping level is equal to or larger than this effective density of states in the conduction band for n-type, if you want to check for p-type, then you have to compare with NV, of course. For n-type, compare with NC. So if your doping level is higher than this, either this or this, then that means your semiconductor starts to be a degenerate semiconductor already. Okay. So you can also check the point when it turns into a degenerate semiconductor when the EF, the Fermi level, is less than 3 kT from band H. Okay, so for example, okay, question for you. If I'm doping my silicon to n-type, so the position of the Fermi level will be less than 3 kT relative to which band H? In comparison to which band H? Is it the EC or EV? If my semiconductor is n-type and I would like to check out on the degeneracy properties, do I check in comparison to EC or EV? Anyone? EC, yeah, EC, yeah, is it EC? So why is it EC? Why do I have to check against EC? So all of you said EC. Why is it EC? Why do you want to check against EC? Faris, why not EV? Kenapa? Any idea? What happens to the Fermi level if you do the doping? Say for n-type, okay? For n-type, okay, so when you dope your silicon to be more n-type, okay, shifted up, right? Good, shifted up. So we discussed yesterday, when you dope your silicon to be more n-type, your EF will slowly move upwards, okay? Say this one, okay, for example, if I can illustrate here, I don't have, okay, for example, if this is your forbidden gap, okay, this is your EC, this is your EV, EC, EV, so this one is your mid gap, right? Mid gap. So your EI is originally here before doping. So when you dope to 1014, it's going to go up a bit, 1016, 1017, 1019, closer and closer and closer to the EC, right? On the other hand, if you dope it to p-type, it's going to go down, 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 1014, 15, 16, 17, 18, closer and closer and closer to EV. So in this case, if you dope your silicon n-type, so you need to check whether or not your EF is less than 3 kT away from your EC, okay? Away from EC. On the other hand, if you dope your silicon to, oh, I have it here actually. It's in the back. Let me draw here. So relative to your band H, yeah? For example, if I can draw here, So EC, EV, EI is the original level before doping. EI is before doping because it's intrinsic. Okay, so if you dope higher and higher and higher, your EF is going to go higher. So up to a point when the distance between EC and EF, your current EF, due to that doping, is less than 3 kT. So the moment it hits 3 kT separation distance, now your semiconductor becomes a degenerate semiconductor due to the high doping. Okay, so you need to check. You need to calculate the kT. For example, if our calculation last time, the kT was what? 26 milli EV, right? 26 milli EV. So that's like 0.026. So you can times 3 in order to get your 3 kT, for example. Okay, you can always check. So as long as it hits 3 kT away from either band edge, now your semiconductor has become a degenerate semiconductor. So what happens next? If you increase your doping level further, your EF will in fact go above EC or below EV. Can also go beyond, can go inside, okay? Can cross the border and go inside the conduction band, states, or valence band. So let's see the next page. So remember, the threshold here will be 3 kT away, okay? 3 kT away and high doping. So this is what means by degenerate semiconductor. Okay, let's look at this. So the left hand side is the N type and the right hand side is the P type. N type on the left, P type on the right. So see the position of your EC and EV, EC, EV. So now what happens to the EF at this point? Apa jadi kat EF? Is it below EC or above EV? Yeah, above, right? So it has gone beyond. It has gone beyond the band edge. Before this, we've discussed where it could sit down here, close to, less than 3 kT away, for example. 3 kT, but now it has gone beyond the limit, beyond the, pardon for my handwriting here. It's gone beyond the edge. Okay, so it's gone up and gone down for P-type. So N-type degenerate semiconductor when your N naught is more than EC, and as a result, your EF will be higher than EC. Sorry, N naught is higher than NC. When N naught is higher than NC, that means your EF is higher than EC. It depends on doping level though, okay? Or for P-type, P naught more than NV, EV higher than EF. So EV now stays higher than EF because EF has gone beyond the band edge, right? So that's a degenerate semiconductor. So once degenerated, the carrier density expression, like density of free electron calculation, cannot be assumed anymore. So you cannot use the previous calculation anymore. Okay, it's only meant for non-degenerate semiconductors. A degenerate semiconductor still has far fewer charge carriers than a true metal. So in terms of the number of carriers, metal has got more than degenerate semiconductor, but degenerate semiconductor has more than non-degenerate semiconductor in terms of number of charge carriers. So its behavior is in many ways intermediate between semiconductor and metal, okay? So if you're talking about electrical conductivity, for example, if going to the right means improve electrical conductivity, then your non-degenerate is here, degenerate is here, and metal is here in terms of a spectrum. So this one improve conductivity to the right. So metal has the most number of charge carriers, followed by degenerate semiconductors, followed by non-degenerate semiconductors, right? So it is still a semiconductor material, but its behavior is like metal, but it's not metal. So degeneracy is often observed in the so-called transparent conductors like zinc oxide, F-dope, fluorine dope tin oxide, or indium tin oxide. So anyone working on indium tin oxide for your FYP? Anybody working on ITO? Anyone working on Z oxide? Quite a number of you, right? So this is an example of a degenerate semiconductor. So try to go and check your material, right? So why do we want degeneracy in transparent conductors? So if you talk about transparent conductors, have you ever heard of transparent conductors? Anyone? No? Okay. No? Siapa pernah dengar? What you call transparent conductors. When do you use transparent conductors? Anyone? Tak pernah dengar. Okay. Hasnain pernah dengar Hasnain? Ever heard of degenerate semiconductors? Or transparent conductors? Transparent conductors? What are the typical conductors that you learned before? What are the typical conductors? What are the examples of conductors? The common ones. Give me some examples. Come. What are typical conductors you learned before? Yeah, okay, gold, copper. What are those? Okay, gold, copper, silver, platinum. So what do you call those? Metals, right? So they are metals. When we talk about conductors, we normally talk about metals. But we also have another form of conductors, which is this, degenerate semiconductors. So it's also a form of conductors, and it's also transparent at the same time. So if you look at metals, are they transparent? Have you ever seen transparent metals? So if they're not transparent, then what are they? How do they look like? If not transparent, then they are opaque. Yep, opaque. What else? So if you look at, if I have a metal coating on my substrate, whatever it is, silicon or glass or whatever, how does it look like? Opaque, and what else? Shiny, right? Yeah, shiny, opaque. So those are the conventional look of our conductors, right? So we want, if you want to integrate your conductors for certain applications, for example, let me give you an example. If you talk about, if you want to integrate your device on your conductors on Windows, for example, in order to be solar windows, if you like, would you like your windows to be opaque and shiny? If you're working inside, so I'm now in my office, I'm working inside, are you okay to work in a shiny and opaque space? If you look, can you look through the window if it's opaque? Can you see all the trees out there in front of School of Physics? Can you see what Pusat Sejahtera? Cannot, right? It's opaque. It's opaque and it's shiny. So if it's shiny, what does it mean? It's going to reflect light to you, right? If you turn on the lights inside your office, then the light's going to be reflected all over into your eyes. And can you work like that? Cannot, right? So you want it to be transparent because it's a window anyway. So if you want to integrate your device, for example, a solar cell on Windows, you want the windows to be transparent, and also what else? You want it to be a solar cell on Windows. So you want your windows to be transparent and apa? What is the other word? Transparent and 1028. Absorbing light, yep. Transparent and also conductive, right? So just imagine if you want to integrate your device on Windows. I'm looking at my Windows now. So you want your device to be transparent and conductive at the same time in order to carry charge carriers, carry electricity and stuff like that. At the same time, you want it to be transparent. So this is the use of transparent conductive oxide. One of the many more examples, okay? So in that sense, you want it to be transparent and yet conductive. So if you look at your windows now, are they transparent? Look at your windows. If you're in a building now, look at your windows. Are they transparent? Yes. Are they conductive? No, right? So they are just normal windows, right? So they are. So what are they? What are your windows on the spectrum of metals, insulators, semiconductors? The first topic that we learned last time. So what is your window in the spectrum? What is your window in the spectrum? Insulator, right? The window is an insulator. It's made of silicon dioxide. So SiO2. It's an insulator. So it cannot conduct electricity. So you can turn the very same windows as solar cell as well. So what you need is you can integrate transparent conductive oxide on your windows, but you have to make sure that your material, in that case, transparent conductive oxide, has to be transparent and also conductive. Okay, then only you can make it as solar windows, right? Transparent and conductive. So this is one of the what we call main properties of degenerate semiconductors: transparent and conductive. So that's why we call it transparent conductors. We even call it as TCO in general, a class of material in which it is both transparent and conductive, and yet it is oxide, right? When you talk about oxide, typically are they conductors? If you talk about oxide in general, are they conductors or are they insulators? Generally, insulators, right? Just like what Go said, Juaria said, they are insulators. But in this case, a TCO is the opposite. It is transparent yet conductive, and yet it is a form of oxide. So we call it TCO, transparent conductive oxide. And we have many examples of TCO like ITO, TiO2, and many more, right? So transparent conductive oxide. If you look at the doping level inside TCO or transparent conductors like this, so the doping level is typically around 10 to the 19 to the 10 of 20 per centimeter cube. Right, transparent conductive oxide examples like zinc oxide, ITO, tin oxide. So they are both transparent and conductive. So look at its name, transparent conductive oxide. So the typical thickness is 100 to 200 nanometer. So no one is working on ITO or tin oxide. I know zinc oxide, a number of you. You don't use any ITO at all for your FYP, anyone? If you get to it with ITO, have you ever measured the transmission, for example, light transmission through the ITO in order to prove that it's transparent in nature? You can try if you work on ITO. For example, if you have ITO on glass, if you have your ITO, say this one is glass substrate, just like what you see on the left. say if you coat the top of the glass with ITO, for example, with 100 nanometer, you can go to UV visible spectrophotometer in no lab to measure light transmission. Light that's going through the material. Okay, so you will see that the transmission is typically 85% or more in order to be a good transparent conductors. Okay, if the transmission is very low, like 40 or 50, then it's not qualified. It's just too low. It's just not transparent. Okay, so just imagine if you can integrate this TCO on your windows, and if you're driving a car, for example, or if your parents have cars, then you can replace the tinted inside the car made of plastic. You can replace that with transparent conductors. So as you drive, you're actually generating electricity as well, due to the contribution of the solar cell on your windows. So that can be done. In fact, now people is trying to come out with solar cars as well. All right, TCO conduct electricity to external circuit. Applications are like solar cell, flat panel display, touch panel, many more devices, smart windows, okay, and many more applications. So band gap narrowing effect. Okay, next will be band gap narrowing. We've covered a little bit of this when we talk about heavy doping in our last topic, right? Heavy doping, the effects of high temperature and high doping. So this is the very same thing. So it's called band gap narrowing effect. We also discussed about this, BGN, band gap narrowing. We also can say is band gap shrinkage, same thing. Band gap narrowing effect, a phenomenon when a high impurity concentration causes a reduction of the band gap. So we've seen last time. So let's recall. When do you start seeing band gap narrowing effect? At which doping level? From a previous topic. At which level you start seeing BGN? No, I mean in terms of doping level. Is it 10, 16, or 17, or 18, or 19? When you start seeing the effect of band gap narrowing? Usually. Yeah, about 18, right? Well, usually you'll see the effect. You start seeing the effect above 18, above than or equal to 18. If you dope your semiconductor to 16, 17, you won't be seeing significant band gap narrowing effect yet, right? Only if you hit 10, 18 or above, then you'll start seeing the magnitude gets bigger and bigger and bigger, right? So it causes reduction of the band gap. So your effective band gap will be slightly smaller than your original band gap. So the band gap reduction, delta EG, for silicon at room temperature is given by this equation for silicon. So the amount of reduction or delta EG will be given by 22 times N, which is the doping level, over 10 to the 18 square root, right? Milli electron volt. So where the doping is in the per centimeter cube. So for example, if your ND is less than or equal to 1018, the delta EG will be somewhere around 0.022 EV, which is less than 2% of the original band gap of 1.12. So whether or not you're going to see any effects in your device, it's really dependent on the device, whether this 2% is big enough, okay? However, for ND more than NC, so remember last time we've I think last few pages you've seen that your NC was 2.8, right? 2.8. If you can, yeah, NC here is 2.8. If your N now is more than NC, so when the doping is more than your effective density of states in the conduction band for N-type, your delta EG will be more than 0.12 EV. So if you compare 0.02 EV and 0.12, you can see that this 0.12 is now more significant fraction of your band gap. Okay, so reduction will be more pronounced if you dope your if you dope your silicon to more than 1090 or more than the effective density of states. Okay, is it clear so far? Is it okay? Right, I'm just gonna stop here because I'm gonna need to follow a lab audit now. So tomorrow will be what? Tomorrow will be Wednesday. Yeah, tomorrow I'll see you then at 1 to 2 p.m. again. So we're gonna continue to compensated semiconductors. Try to also look into these calculations, this example, and we're gonna discuss tomorrow. Right? Calculation number 1, number 2, number 3. Although the workouts are given already, try to understand what is expected from each question. Okay. All right. So, any questions for today on the degenerate semiconductors? Why need to have oxide? Why for TCO? Why need to have oxide? Okay. Well, it's not the TCO comes after the name of materials which have properties of transparency and conductivity. So dia bukan you have TCO first, then we need to have oxide in order to fit the TCO. It's the oxide first. So we have the oxide, and we discovered that, oh, okay, we actually have some oxides that are transparent and conductive. So therefore, we call them transparent conductive oxide. Okay, so they are they form a special group of oxide out of the typical oxide. So that's why we call them as TCO. So they are there already, then you give them a name. So it's not that we have a name, then we put oxide in that, right? It's the other way around. So we discovered that some of our oxides have good conductivity, good transparency. Okay, let's call them and let's group them and call them TCO. Yeah, that's how it works, right? So you now know that some oxides don't conduct. In fact, generally most oxides don't conduct. And there's a special group called TCO, which conducts electricity well. And at the same time, they are transparent and they can be good conductors. And that's why we incorporate them into various devices, just like what we discussed now. Solar cell, windows, transistors. Well, typically we exploit them for optical applications, right? Because like solar windows, you are doing interaction with light, so that's why we talk about optical application. Like solar windows, solar cell, again, is also another optical application. But it can also be used for non-optical applications. But the TCO thing is exploited for optical applications, mainly. Right? Any other question? Is it okay, Sakina? Okay. All right, cool. Any other questions? Kalau tak, kita habis kat sini ya. I'm gonna need to follow the lab audit now. All right, I'll see you tomorrow then, inshallah, 1 to 2 p.m. We'll continue with compensated semiconductors. Right? Bye-bye. Take care. Assalamualaikum. Stay safe.